Hi guys, today we'll talk about the derivatives. Now, physics doesn't involve a lot of calculus. It uh, it is actually very helpful for physics because without calculus, Newton could not have theorized his findings, and that would lead to a complete I don't know what, because then we would not be here. We would not really know what Newton found, and we would not really know that what he found, even though was correct on a macroscopic level, would actually turn out to be wrong because of a guy named Einstein. And basically, then modern physics won't be here, and the entire future or the present for us would not have been the same. So derivatives is a part of calculus in which we actually tend to find slopes of certain functions. Now, a function could be any continuous line which is represented in this Cartesian plane in between the x and the y axis. And the slope is defined as a tangent. Defined for the tangent and is equal to this angle theta. The tangent of this theta is equal to the slope of the function at the point x, where x would be somewhere here. Now, we need to understand that the tangent is a special kind of, is a special kind of secant. Now, what is a secant? Alright, secant for a function is basically if we have two different points, say x and then say x naught or x sub 0, and we define another point, say x sub 0 plus delta x. Now for these 2 points, a secant would be a line going through both of them. So this is a straight line which passes through f x naught and which passes through f x naught plus delta x. And this would be the secant. Now imagine I make this delta x very small. Delta x is actually this distance. So if I make this distance really small, I would end up with the secant going like this, then like this, and ultimately like this. So it would end up at a specific slope. That is, this would be therefore my specific slope. The reason I'm calling this specific line as my specific slope, I use the word specific because as delta x tends to 0, it gives us a line. It does not give us an indeterminate value. That is some kind of a line that we are unable to define or unable to find a slope for. But in this case, well, in many cases we'll get a tangent, and that secant will actually turn into a tangent. And this is very much fundamental in calculus. Now, therefore, I would define for the slope of the tangent to be, that is, the specific slope would be equal to the limit delta x tends to 0 when we divide this difference And how did I get this? Well, because if we really magnify what is actually happening in this picture right here, is that we end up with the slope, and these 2 points would represent my 2 points on the curve, which is separated by a distance delta x, and the difference in the height would be f of x naught plus delta x minus f of x naught. And so, because this is a right angle triangle, I can define what tangent of theta is. That is the perpendicular divided by the base, or this value divided by this value, and that ends up giving me this. So in other words, the specific slope that I found out would be limit when delta x tends to 0, that is, this distance goes on to become really small, and we get this ratio. So if I'm able to evaluate it, which I'm able to because this gives me a very specific determinate slope, that is a slope for which I can calculate a specific tangent of the angle that it makes with the positive x-axis, and this is known as the derivative of the function. And this forms the basis of differential calculus. Now, let us start with a very specific function, y equals x square, and for that, for us to calculate the slope, the specific slope of this function for any given x, we will first have to draw it to get a better view of the problem. Now, I do understand that x square, or for any rational number or any number, the square of it would actually give me a positive number. Therefore, y always has to be positive, and in that case, we could say for every positive y we would have x. In this case, we'll have 2x. So no negative value of y would satisfy this equation. That is, no negative value of y would be a part of this function. So y, this is my y-axis, this is my x-axis, this would be a parabola which opens upwards. Its vertex would be at the origin, and it is symmetrical about the y-axis. Now, just to make the case a bit more simple, what I would do is I would make that I would only think about the function for a positive x. So I can eliminate this part or this region of the curve when I calculate, given that x is greater or equal to 0. So this is an external condition that I've imposed, which only restricts me to deal with this function only, this part of this function. Now, for this I have to calculate the derivative. Now, I know the function, the formula, that the derivative of any function would actually be y evaluated at x naught plus delta x minus y evaluated at x naught divided by delta x, when delta x tends to 0. So when we have x naught plus delta x in place of x, we would actually get x naught plus delta x whole square minus, and when we have x naught in place of x, we would get y to be equal to x square, and we divide this by delta x. We always write this condition, the delta x always tends to 0, because this gives us a better approximation of what we will do right now. Alright, now we can open this using, or we can solve this using three formulas. The first one would be a square minus b square. I would write the formula right here. It's a square minus b square, which is equal to a plus b times the difference a minus b. Or I can say a plus b whole square would be equal to a square plus b square plus 2ab. Or, well, this would be the same thing, but I can expand this using the binomial theorem. The binomial theorem is basically stating this again, but for a more generalized power. Well, in that case it could be n, where n could be any rational number. We'll not discuss that, but we just need to solve this. So we would start with using any of them. I would use, say, the square formula, and I would end up with x naught square plus delta x square plus 2x naught delta x minus x naught square divided by delta x. Now, I know this is just the negative of it, so I can cancel it out. Now, I have two terms, so if in the numerator, now divide the denominator with these two terms, and I end up with delta x square by delta x, that is this, which will give me delta x. Limit delta x tends to 0. Plus, this divided by this would give me 2x naught. Now, the important thing here is that we have assumed that delta x limits, that is, it approaches 0, it is not equal to 0. Therefore, delta x by delta x can be cancelled, and we can say this is equal to 1. We know this operation is only valid when the denominator is not 0, and hence that would imply that numerator must also not be 0. So, because this is not equal to 0, we were able to cancel delta x from there. Now we have to add a finite term with an infinitesimally small number, and that small number is so incredibly small that we neglect it at this stage, because it's saying 10 plus, suppose this is 5, so it would be 2 times 5, that is 10, plus delta x, and delta x approaches 0, so we could say delta x can be very approximately taken as 0.00010 times 1. Well, that would still be a bigger number, because we can add a 0 and then we can write 1. And we can do that basically infinite times. So we will end up with a smaller and a smaller and a smaller number, but we will still not get 0. Now that indicates that this term is so bloody small that we have to eliminate it. So finally this gets cancelled in a way because we are neglecting it, and this ends up with 2x naught. Why? Because delta x was very small compared to 2 by x. Remember, when we have addition, we are comparing them, but it is not that much of a relative comparison that we do when we are dividing them. So the derivative of y is equal to x squared is also written as dy by dx, happens to be 2x, and this is how we calculate the derivative. Thank you, and please subscribe. The link is in the description of my email, and if you have any problems or any queries, please do inform me via my website. Thank you.